Hi student, here I'm going to give you another revision once again, the same one we covered in the class last time, but this will be much simpler. Well, I advise you to write down notes from this slide and take it with you to the final exam, plus all the well, I send you some graphs. You can take this one with you to the class once again. Actually, you can take everything with you to the class, but I don't want you to get a mass work paper with you. Just try to be neat, clear, and know what you take with you and how to use it on time. So first we're going to start with the question about the AGVs, was part of the assignment number 6. So you remember that we had this table below, and which contain all the movement between the stations A, B, C, and D, and when the carriage is going to be loaded or unloaded. So something similar here. We are going to have the timing and the for the loading and unloading, which is 0.45 minutes, and each vehicle speed was something about 1.4 meter per second. The total loads of 43 loads into the system at station A and 30 loads exit station A. In addition, during each hour, 6 loads exit the system at station B and 7 loads exit the system from the station D. And that's why we have the 13 empty trips made by the vehicles within the AGVs. So we would like to know how many vehicles are required to satisfy these delivery requirements, assuming that the traffic factor of 0.85 and the availability of 0.95. And once again, I have to remind you that if we are going to have an efficiency, we are going to use it. If not, we are going to consider it as unity 1. Okay, so first step is we are going to put the table in front of us. We are going to calculate first the LD. So taking all the loaded time. So as you can see here, we have the first row from A to B, from A to C, from A to D, from C to B, from D to A, and from C to D. So by adding all these values using this equation, we multiply first the 19L by 95, then the 10L by 80 plus the 15L by 150, the 12L by 65 plus 22L by 80 plus 30L by 150. Then at the denominator we are going to have the 18L plus 10L plus 15L plus 12L plus 22L plus 30L. So the next step, we are going to find the answer for the LD, which is going to be 110.28 meters. Then we are going to go to calculate the time when it's going to be an empty loaded. So the empty loaded, we have only 2 carriages, which are the 6E over 95 and the 7E over 150. So we are going to do the same thing at the top, but at the bottom we are going to use the same 107 we got when we had calculated the loads for the loaded carriages. So the LE value is going to be 6 multiplied by 95 plus 7 multiplied by 150 divided by 107. And the figure is going to be 15.14 meter. Now, to find the TC, the time required is going to be 0.45, which is the loading time for the vehicle, plus 110.28, which is the LD, divided by the velocity, the speed of the carriage, 1.4 multiplied by 60, because it's 1.4 meter per second. If we are going to multiply it by 60, we are going to change it to minute. And then we are going to have unloading time, then the LE divided by the speed once again. And the total time is going to be 2.393 minutes. WL is going to be the 107, calculated by adding the loaded carriages, multiplied by this time, which is the TC. and we are going to have 256.04 minutes of work required per hour to complete all the deliveries. The AT value is going to be 60 multiplied by 0.85 multiplied by 0.95 that we had from the availability and the other stuff. So if we are going to have an efficiency, then we have to add it in this equation. And the AT value is going to be 48.45 minutes per hour per vehicle required to do all the deliveries. So simply to find the number of the vehicles, we just simply divide the 256, which is WL, multiplied by the 48.45, which is the AT, and we are going to find that the number of the vehicles required is going to be 5.28. Of course, we need more than 5, so we are going to round it up to 6 vehicles required. Okay, now this will be the first question, which is question number 2 in the assignment number 6. Sorry. One of a similar question is going to be given to you in the final exam. The same way of calculation will be used. Now, the calculation of a Hooper geometry of mass for mass flow. This is the same example we had, but this one is more clear. Once again, as I told you, you are going to have similar question in the final exam, so you have to calculate what is the Hooper designed conical and what will be the diameter required to empty this Hooper design. Now, I just discovered today that we may have a problem. Well, it's a type of miss in the final exam. The value for the angle was 18, and actually you have to use 28. I'll try to come to the exam and declare that in the exam as well. So in this example, we had the wall fraction angle was phi was 25 degree. The bulk density rho is 352.41 kilogram per cubic meter. The angle of internal fraction were 50 degree, and the flow function is sigma c is equal to 0.3 sigma 1 plus 4.3. So as we mentioned earlier, that these values for the sigmas are in pound force by foot square. So using the design chart for conical hoppers of phi is equal to 25 degree. From 25 degree, we go to the line where we're going to have the sigma is equal to 50. So delta is equal to 50. Then we go down all the way to find the semi-included angle in degree, which is going to be something about 17.5 degree here. And then we can get the value of the FF flow factor, which is going to be at D50. Once again, we are going to cross the line to have the value of 1.27. So we got 17 or 17.5 here, and we got the FF value of 1.27. So we go to calculate the value of the H theta, which is calculated by using the equation 2 plus theta, which has been found from the chart, divided by 60. So 2 plus 17 divided by 60, which is equal to 2.284 for the H theta. Now, we have to find the value for the diameter, B. So we start to calculate for the FF is equal to, the flow factor is equal to the sigma divided by the sigma A. Then we are going to find that the sigma A is equal to sigma divided by the fraction factor. The condition for no arching for the Hooper is that the sigma A should be more than the sigma critical. Then we use the equation we had, substitute the value for the sigma A, which is equal to sigma divided by this fraction factor, as we can see here, and is equal to 0.3 sigma 1 plus 4.3, or by substituting the value of the FF of 1.27, we will have that sigma divided by 1.27 is equal to 0.3 sigma 1 plus 4.3. So in this case, we are going to consider that the sigma is equal to sigma 1, and we are going to substitute, we are going to change the value of 0.3 sigma 1 to the other side, and then we are going to have sigma divided by 1.27 minus 0.3 sigma 1 is equal to 4.3. By substituting this value, we can find that the sigma 1 is going to be equal to 8.82 pound force per foot square. Then sigma critical is simply by using the equation we had at the top there. So just divide by the fraction factor, and then we are going to find that the value of the critical sigma is going to be 6.95 pound force divided by the feet square. Now we need to find the value of the diameter, so we are going to apply the equation we had in the lecture notes. It's going to be the h theta multiplied by the sigma critical. 47.88 is the factor to change the sigma critical value from pound force per foot square into Pascal, which is Newton over meter square. Then everything is going to be divided by the density multiplied by 9.81, which is the gravity acceleration. And by substituting this value, you can find that the B value is going to be equal to 0.22 meters, which is going to be something about 22 centimeters. Now, once again, the 47.88 is to change from pound force per foot square to Pascal, which is in Newton over meter square. If we are going to check about the units, you can see that this one is unitless, the h theta. The 6.95 multiplied by 47.88 is going to be Newton over meter square, and the denominator we are going to have the kilogram per cubic meter multiplied by 9.81 meter per second square, and this will change it into in Newton. So we are going to have a Newton over Newton meter. If we are going to change Newton over cubic meter, sorry, then if we are going to have Newton over meter square and cubic meter over Newton over cubic meter, and by subtracting, we are going to have just meter as the main unit for the B value. For the screw conveyor, I just colored the part required for you in the final exam to do this question. So as you can see, this is the part we showed you last time on the presentation board. In the assignment number 3, we had the screw conveyor with limestone dust of at 35 ton per hour rate, the 12 meter length, 45 degree inclined. We have 1800 RPM motor and connected to a double reduction shaft mounted to a speed reducer. So we were required to calculate the power. We are not required to calculate the power tomorrow. So first we have to go to the property table. For the limestone dust, we are going to have the density bulk is equal to 55 till 95 pound per cubic feet. So we are going to use, in this solution, we are going to use 80 pound per cubic feet for the solution. The material code is 75, which is the density, multiplied by A46, which is the code for the material, my. So the conveying load is going to be 30B from the table, and this will tell you exactly what will be the percentage of the filling of the screw conveyor. The material code is given, Fm is equal to 1.8, and the component group is 2D. All these data can be get from the table, but in the exam tomorrow, I can give you exactly what will be the properties of the material you are going to use. The material code will be missing. If the material code will be missing, just use the A46 value as A35. So your code is going to be, for example, if I are going to use the same material, is going to be 75A35. And this will guide you how we are going to find the diameter required for the screw conveyor. So to the solution, we have to follow the notes. We had the Q value is equal to 35 tons per hour. That's in the question you had. The bulk density is 80 pounds per cubic feet. And for the Q value, 35 tons per hour can be simply changed into pounds per hour by multiplying by 2,204. Well, you have to double check this value. It's 2,200. So 35 multiplied by 2,200, we're going to have, sorry, it's just 2.204. 2.204. So 35 ton, changing it into kilogram, where I have to make it 35,000 multiplied by 2.2, we are going to have 77,161.79 pounds per hour. The nominal capacity is going to be how many cubic feet we are going to move each hour. So we have to divide the value of the Q from a mass per time divided by the density, which is the mass per volume. So we are going to have at the end how much volume we are going to convey each hour. So simply divide the Q value, which is 77,161.79, divided by 80, which is pound per cubic feet. And this will give us 964.522 cubic feet per hour. Now, at this stage, this is the nominal capacity, but we said earlier that we should have a safety factor before we are going to use this value. So the equivalent capacity is going to be the nominal capacity multiplied by the safety factor CFO. And we said that the safety factor is going to be something between 1.2 to 1.4, so we are going to go to 1.2. So it's 1.1 to 1.2, so we are going to go to the maximum of 1.2. Then multiply the 964.5 by 1.2, then we're going to have 1,157.42 cubic feet per hour. I hope it's clear at this stage, and then we are going to go to the next station. So we have the equivalent capacity. We got earlier what is the material code. We had the A46 for the material code. Then we will be able to find what's the diameter we have to use. So going to these tables, the material class code is A46. That means we have to use this one. Now, I told you tomorrow in the exam, you can use the A35, so you can go to the table at the top right side. From here, we have two values for the capacity. It's either 1040 or 1400. Because we have something between them, we're not going to use the minimum value, we are going to go to the upper value. So we have 1140, so we are going to use the 1400 cubic feet per hour. From there, we can find all the values required. The screw diameter in inches is going to be 16 inches. And the maximum RPM is 45 RPM. And at 1 RPM, we will be able to move 31.2 cubic feet per hour. Okay, now the three values we are going to use later to finalize the solution. This diameter, 16 inches, this will be part of your answer. The maximum RPM, 45, we are going to check the calculated RPM against the maximum RPM. And at 1 RPM, how many cubic feet per hour we are going to convey. So, from the tables, at 30B, conveying load, and a C of 1,157, we choose the screw diameter of 16 inches because we have the A46. The maximum RPM is 45 RPM, and the maximum capacity was 1,400 cubic feet per hour. And at 1 RPM, we are going to convey 31.2 cubic feet per hour. So we said that C1 is equal to 31.2, So to find the RPM, simply we are going to get the equivalent conveyance value, the C, which is the QM multiplied by the CFO, divided by the C1. So we are going to have the 1157.42 divided by 31.2, and we are going to find this 31.1 RPM is the answer to convey the material at the rate of 25 tons per hour. Now, to check if this one is acceptable, the RPM we had is the RPM we had as a maximum RPM, which was 45, is more than the M value we got in the calculation. That means that the 16-inch diameter screw, we are going to be suitable to do the work for us. Okay, now at this stage, this will be your final answer where you are going to get the marks for. Now, the question for the hydraulic conveyor, it has been repeated many times. I can send you the answer for the full question, which is the best answer I got in the assignment, which done by John Lim. But we are going to concentrate on this one because actually that's what we are going to do the final exam. So you will have the same table you had in the assignment, but with different values. We are going to have how many tons per hour of the material we are going to convey. The specific gravity will be given, the average particle size will be given, the concentration of the solids in the liquids will be given, and the static discharge is not going to be used in this time because we are not going to calculate any power. So the points 1, 2, 3, and 4 are going to be the only useful point for us in the final exam. So first we have to find I should remove this one. So the quantity to be pumped but determined by the issue is, we said that the weight of the solid in the slurry is 65 tons because that's what we are going to pump per hour. The weight of volume of water equal to the solid volume is equal to 65 divided by the 2.65. Now 2.65 is the specific gravity we had. So we found the number of the weight of the volume of water equal to the solid volume is equal to 24.5 ton. The weight of the water in the slurry, we had this one, CW, is given as 30%. So to find what will be the tons of the weight of the water in the slurry, we are going to do the 65, which is the solid weight in the slurry, multiplied by 100 minus 30, which is the concentration, divided all by 30. So we are going to have 151.7 tons. To find the total weight of the equal volume of the water, we are going to add the 151.7, which is the weight of the water in the slurry, plus 24.5, which is the weight of the volume of the water equal to the solid volume, which is 24.5 tons. So the total is going to be 176.2 tons. The total weight of the slurry mixture is going to be the 65, which is the weight of the solid in the slurry, plus the 151.7, which is the weight of the water in the slurry. Because you know that the mixture consists of water and the solid, and that will be the total mass we are going to have for both the solid and the liquid material. So to find the specific gravity of the slurry mixture, we have to divide the 216.7, which is the total weight of the slurry mixture, by 176.2. The one which has been calculated was the total weight of the equal volume of water for the material. Then the concentration of the solid by the volume, CV, the new calculated one, is going to be the 100 divided by 176.2 multiplied by 24.5, which is going to be 13.9%. Now we need to find what will be the flow rate in liter per second. So simply the quantity of the slurry is going to be the 176.2, which is the total weight of equal volume of water. It's in cubic meter per hour, and then we can change this one to liter per second. Now the how change this one from tons per hour into cubic meter per hour, because it's water. So the water density is 1000, and thus we can say it's 1 cubic meter per ton, and then we just simply say that the quantity of the slurry, by using the equivalent weight of the water to volume, we are going to change it to cubic meter per hour. Now, cubic meter per hour, to change it into liter per second, we only have to divide it by 3.6, because simply we said, okay, now we're going to change the cubic meter to liters. We multiply by 1000, then divide by 3600. So it's going to be simply by dividing by 3.6. So 176.2 divided by 3.6 is going to be 49 liter per second. So given the diameter of the pipe is 150 millimeters, you are going to be given a different diameter. Of course, it's going to be different flow rate, different specific volume, but you are going to follow the same steps. A 150 millimeter pipeline is selected in this question. So to check the slurry mixture velocity, the actual one, simply divide the Q in liter per second multiplied by 1273, all divided by the D square. The D is the pipe diameter in millimeters, and it's in this case 150 millimeters. So complete the calculation. The velocity in this case will be 49 multiplied by 1273 divided by 150 square, and it's going to be equal to 2.8 meter per second. Now, that will be the actual velocity required to pump the slurry mixture inside the 150 milliliter pipeline. We have to check by using the Drown's equations from appendix number 5 to find the limiting settling velocity. So the V, which is limiting settling velocity, is going to be equal to the FL multiplied by under square root of the 2GD multiplied by the S minus SL divided by the SL. Now the SL value is given above was 1.2. So for simplicity, we are going to use this one as 1, and that's what we are going to see next page. But first we start from the figure 852. I send you this figure, just print it and bring it with you to the final exam. You can see on the upright left axis, we can find the parameter at the FL value. And at the x-axis, you can find the average particle size. And here we can see that the CV value given. Okay, now the CV value is calculated, and we found it is going to be 13.9%. The D50 is equal to 212 microns. So we have two knowns, and we can find the FL value. So first, we find the value of the average particle size, 211. Then we draw a line to the 13%. So I took the 10% approximately. If you are going to get something above 15%, go to the 20%. Sketch a line, sketch another line, and you will find that the value is going to be something about 104. Okay, I choose as 104. If anyone can read with his own eye, it's going to be a different value, but it's going to be not more than 1 or 5 anyway, because this is 1 and this is 1.1. So the FL value is 104 in this case, and by substituting all the values in the Drown's equation, we can find that the V is equal to 104 multiplied by the under square root of 2G multiplied by 0.15, which is the diameter in meter this time, multiplied by 2.65, which is the actual specific volume minus 1 divided by 1, and the velocity is going to be equal to 2.3 meter per second. Now we said here that the 150 millimeter pipe therefore is considered suitable for this application, since the limiting settling velocity, which we calculate as 2.3 meter per second, is lower than the actual slurry mixture velocity, which is 2.8 meter per second. So this is the only condition where we can have a suitability for the pipe if the V limiting velocity is less than the actual slurry mixture velocity. Otherwise, you only going to say that this pipe is not suitable. That's mean in the case where we're going to have the VL is more than the actual velocity. Now, for the mass calculation, this will be something. That's the example we had in the class. Okay. Now, the material we're going to use maybe is going to be the same I told you about, so you can use simply the same density we're going to use in this example. So we have the ideal spacing even over the weighing region of 1,800 millimeter, and the effective build width is 600 millimeter, and the feed intended to be 460 ton per hour. Now that's what we want it to be. Okay, so everything we should have should be about or more than the 460 ton per hour. So we have to determine the following actual parameters, and that's what we are going to cover soon. So you can see here we have a table. It's not something like what we had in the assignment question. So we had indicated load in kilograms, and we have the build speed. We had 8 values for readings, different velocities and different weight each time. So in this case, we said we have to calculate the average of all these values. So we are going to have the average load, and we are going to have the average velocity, and then we can use it to solve the question. So the first stage we are going to have is to have the average values for both. Well, just ignore the lower row. It's not required. We found that 89.5 kilogram is the indicated load average, and the build speed average is going to be 2.64 meter per second. And this is the description of the diagram we're looking for. So now what we have to find is the edge value, which is the height of the material over the belt. So we don't know what is the height, but we know what is the mass, and we know what is density. So we have the base of the material because we have the length and we have the weight. Multiplied by the edge, we can get the volume. So we know that the mass is equal to density multiplied by the volume. The density is considered to be 1,360 kilogram per cubic meter. So the volume is equal to the length multiplied by the height multiplied by the width. In this case, the width is given, the length is given, but the height is unknown. So we can rewrite the equation of the mass by using the known values and keep the unknown as it is. So the volume multiplied by the density. The volume is 0.6 meters, which is the width, multiplied by 1.8 meter, which is the length, multiplied by the h. Everything multiplied by the 1,360 kilogram per cubic meter, and then we are going to have that the weight as a function of h is going to be the W is equal to 1,468.8 h. So whatever the value of h is going to increase, the value of the mass is going to increase, and vice versa. So first, to find the value of the h, the 89.5, which is the average mass we got, is equal to the 1,468.8 h. So we can see that we have the mass in kilogram, and we don't know what the value of the h. So the h is going to be equal to the 89.95 divided by the 1,468.8. And we found it here to be 0.0609 meters, which is equal to 61 millimeters. Second, to find the Q value, which is how much volume flow rate we are going to move each second over the belt. We know the velocity, which is the average velocity we calculated, 2.64 And A is the cross section of the material which moving over the belt, which is equal to the width multiplied by the height. So the width is 0.6 meters multiplied by 0.06909 meters, and we're going to find that the Q value is going to be equal to 0.0965 cubic meter per second. For the mass, okay, how the mass flow rate is going to be the Q value, how many cubic meter per second, multiplied by the density, which is cubic meter, a kilogram per cubic meter. Then we can simplify the cubic meters just to find how many kilogram per second we are going to move. So the density multiplied by the volume flow rate is going to be equal to 131.24 kilogram per second volume flow rate. To change this one into tons per hour, we multiply it by 3.6, and we are going to find 472.64 tons per hour, which is more than the 460 required for the design. Now, for the pneumatic pumping, now you know this is not my subject, but I studied thoroughly, and actually the final exam question is going to be something similar. I gave you some of the information in the class about the density you are going to use and the other things, and anyway I'll try to be in the class tomorrow and repeat these things for you. But now let's start to read what we have here. So we had similar system according to the following. Okay, so we had the particle bulk properties of the material. D50 is 300 micromillimeters and the density of 1000 kilogram per cubic meter. The loose pore bulk density is equal to 400 kilogram per cubic meter. The conveying rate, mass flow rate, is equal to 21 ton per hour. Now the case we are going to have in the example I show you in the class is 16 ton per hour. The total length of the conveying pipeline is 220 meter. The internal diameter of the conveying pipe is 102 millimeters. The total pipeline air pressure drop delta P is equal to 60 kilopascal. Type of the feeder, which is drop through rotary valve, which is maximum rotor speed of 40 rpm. The air pressure inside the feed pin on the top of the rotary valve is equal to 0 kilopascal, and the air pressure inside the receiving pin at the end of the pipeline at the end is equal to 5 kilopascal. The mass flow rate of the air flowing through the pipeline, MF, is equal to 0.25 kilogram per second. The conveying air temperature is 50 degrees. The atmospheric air pressure is 101 kilopascal. The atmospheric air temperature is the ambient temperature of 20 degrees, and the gas constant for the air is R equal to 287.1 Newton meter per kilogram Kelvin. By using the continuity equation and the ideal gas law, determine what the superficial air velocity at the feed point VFI, the inlet, at the end of the pipe VFE. Now just to remind you about the continuity equation of the ideal gas, we're talking about the equation of the MRT. PV is equal to the MRT. If we remove the M, we are going to have the P, pressure, multiplied by the specific volume, is equal to the R multiplied by T. So first we have to find the pressure under the feed valve. So it's going to be 101 plus 5 plus 60. Now the 101 is the atmospheric pressure, the 5 is the pressure we had at the end, and the 60 is going to be the pressure drop across the line. So the PI is going to be 166 kilopascal. The R value is given. The TI, we have to change the temperature from degree into Kelvin. So it's 273 plus 50 is equal to 323 Kelvin. Now to find the density, which is 1 over the specific volume, we said that the P, pressure, multiplied by the specific volume is equal to the R, gas constant, multiplied by the temperature. So to find the density, we have to put 1 over specific volume. It's equal to the Pi divided by the RT. Substitute all the values you have above for the pressure, the gas constant, and the temperature, and we can find that the density is going to be 1.79 kilogram per cubic meter. Now, to find the pressure at the exit, the pressure under the feed valve is going to be just the atmospheric pressure plus 5, and it's going to be 106 kilopascal. Do the same operation once again, and we can see that the density is going to be 1.143 kilogram per cubic meter. The MF is given, which is 0.25 kilogram per second, and the QFI in this case is going to be how many kilogram per second we are moving divided by the density, and it's going to be equal to 0.140 cubic meter per second. Now, to find the velocity, we simply divide the Q by the area. Now we know the diameter of the pipe, we can find the area. So the velocity is equal to 0.14 divided by the area, and we can find that it's going to be equal to 17.091 meter per second. And at the exit, we are going to do the same thing, and we can find that the velocity is going to be 26.766. Now, the other part, these values are going to give you something about half of the question marks, and we have to do the rest of the question which we covered last week. So that's what we are going to do. We said that the density for the cement is 1,240 kilogram per cubic meter. 95% size equal to 0.09 millimeters. We assume that the D50 is equal to 0.05. That's the properties of the material. So for the figure, which I couldn't supply for you, so as I told you, use the alpha, which is equal to 0.55, which is unitless, and the N 40 RPM is given in the question, and the D is equal to 0.05. So simply use the equation number 6. What do you need in the equation number 6? The MS, which is the massive flow rate. We said that the massive flow rate is 16,000 kilogram per hour, is equal to alpha multiplied by the density of the bulk material. Now this is not the density of the air and the material, the one we calculated in the section number 1. Now in this case, it is density of the bulk material, which is 1,240 kilogram per cubic meter, multiplied by the value we need to find, and multiplied by the N, which is 40. So to find the value, just simply reuse the lambda equation. Psi equation is equal to the M dot S divided by alpha multiplied by rho multiplied by N. Now we have to remember something. We have the M value is in RPM, radius, so it's per minute, it's revolution per minute. Now the massive flow rate we have is 16 ton per hour, so you have to unify all the units. So you have to change the 16,000 kilogram per hour into 16,000 kilogram divided by 60 to make it how many kilogram per minute we are going to have as a mass flow rate. The alpha is 0.55, the raw bulk remain as 1,240 kilogram per cubic meter, and the N is going to be 40, and you can find the value of the psi. Okay, and that will be the second part of the question, where you are going to have the full mark for it. Okay, I think this will be the last slide we have in this revision, and we covered all the questions we are going to have in the final exam and what we have solved earlier in the revision. The figures are going to be different, some different things are going to be given. You have to write down the notes on the paper, you have to write down as much as you can with your own hand how to make the solution simple for you, because you don't have to follow the same step I did. The most important thing in any solution, you are going to have a solution book with 8 pages. You only have to answer 5 questions out of the 6 questions you will be given. Try to give me a neat answers. Don't make it just writing out everywhere. Just make it very neat, very clear, and so the markers will be able to give you marks according to what you wrote. Don't let them guess if it's right or wrong. Okay. Well, if you need anything, just send me an email. I'm going to upload this video soon to the YouTube. Actually, I'm going to see it by now.